Good morning, dear students. We will start the new chapter, Kinetic Theory. The kinetic theory basically gives an idea of how do the gases behave. So we are going to study about the behavior of gases in this chapter. Let us move on to the topics which we are going to study. Firstly, the introduction part where we will discussing about the contribution of many scientists, actually Boyle's law, Charles' law, and Dalton's law, Avogadro's law. These all laws we will be studying. We will study the behavior of gases, actually the equation, the ideal gas equation, and then we'll move on to the Maxwell's kinetic theory of an ideal gas. Here the greatest contribution of Maxwell key when the molecules are moving, then they having some energy and it is satisfying the ideal gas equation. We'll study the law of equipartition of energy, the specific heat, and the mean free path, the average distance a molecule travels between two successive collisions, like this. Now let us move on to the first point, which is introduction. Basically, who developed this kinetic theory? As the name suggests, kinetic means motion. It was developed by the famous scientist Maxwell and Boltzmann. So kinetic theory, it explains the behavior of gases, and it assumes that gases particles are randomly moving. Okay, now what is an ideal gas? Ideal gas is the gas which is, you can say, a perfect gas which all satisfies the laws which we have studied, Boyle's law, Charles' law, and there is one Gay-Lussac law. Before going ahead, we'll first have to assume that the ideal gas is having some properties. We have to take an assumption that molecule of an ideal gas is a point mass, not a very big size object, and there is no force of attraction or repulsion amongst the molecules. Means the molecules are not having any intermolecular force of attraction between them. They are just colliding with each other, and this collision is elastic, perfectly elastic. I can show you this in the figure. Here, as you can see, the container is filled with there are lots of the molecules, and these molecules are randomly moving in all directions, and they are constantly moving. In this process, they might come closer to another molecule, then they would interact, their velocity will change, and the interaction is called collision. During this, they try to collide with each other and with the walls. So we have to assume that the collision is perfectly elastic. Before going ahead, we have to first understand the how equation of state of an ideal gas, PV is equals to mu RT. This came, you have already studied previously. Let me start with the very beginning. See, there was one scientist which you already know. He was Mr. Boyle. So Boyle, he gave a law in 1662. The Boyle's law was in 1600. Many years back he gave a law that if you squeeze a gas, then volume decrease. If you just take a container and you fill it with gas, and if you try to squeeze it, then what happens? The volume will decrease. Means if you increase the pressure, the volume decrease. This is what Boyle's law. Or you can say pressure is inversely proportional to volume. It implies PV is equals to constant. Okay. Then after Boyle's, there was another law which was Charles' law. Okay. The Charles' law was the volume of a gas increases if you heat it up. Means as temperature increase, as you heat up a gas, it expands. As you heat a gas, it expands. Means temperature increase, volume increase. Or you can say that volume is directly proportional to temperature, or you can say V by T is constant. Then after Boyle's and Charles, there one comes the Avogadro's law. The Avogadro's law is more interestingly, he gave the law in 1811, much after the Boyle's law and Charles' law. He gave an assumption a hypothesis, you can say, not an assumption. He gave an hypothesis, an idea that equal volume contains equal number of molecules. Equal volume of any gas, equal volume of any different gases contains equal number of molecules. Okay, contains equal number of molecules. Let me move ahead. Now there was one scientist called Clapeyron. What did he merged, he combined all these three: Boyle's law, he combined Charles' law, and the Avogadro's law, and he made a very famous equation called ideal gas equation, which is given by PV is equals to mu RT. PV is equals to mu RT. So here we will start with this ideal gas equation. All right. See, the ideal gas equation, it is a relationship. It gives a relationship between the pressure, volume, and the absolute temperature. T is the absolute temperature, which is measured in Kelvin. It is called the equation of state, or an ideal gas equation, which you all know very well, where mu is the number of moles, not number of molecules, and R is called the gas constant, whose value is 8.31 joule per mole Kelvin. Dear students, there can be three different ways you can write the values of the ideal gas equation. Before going ahead, let us have some basic knowledge of this ideal gas equation in detail. See, the ideal gas equation, which was the work of Clapeyron, is PV is equals to mu RT. Here mu is the number of moles. Mu is the number of moles. Before going ahead, let me recall what is mole concept. The mole concept is related to the scientist Emilio Avogadro. See, any substance, if you take 1 mole of any substance, is having 1 mole value is 6.02 into 10 raised to the power 23. You all know very well, it is 1 mole value. See, the 1 mole, if you take a molar mass of any substance, it is having 1 mole of molecules. For example, the mole concept says, if you take oxygen atom, it is a diatomic molecule O2, and oxygen gas you are talking about, not O is not possible, O2 is possible, because it is a diatomic molecule. Okay, single atom is not possible. See, the oxygen atomic number is 8, and the mass number is 16, but if you talk about O2, then mass number is 32. If you take 32 gram of oxygen gas, then it is having 1 mole oxygen molecules. Okay, it is mole concept. I want to make it more clear. 32 gram oxygen is made up of 6.02 10 raised to the power 23 oxygen atoms, diatomic molecules, you can say. So it is mole concept. Every molar mass, if you take any molar mass of any substance, is having 1 mole of particles of that atoms, molecules, or you can say the particles. It is a mole concept. You have to remember it, and you have to make notes along with me. See, if I say what is now ideal gas equation, it is equals to PV is equals to mu RT. Here mu is the number of moles. I can write this equation as PV is equals to the second form is N, number of molecules, into Kb, it is a Boltzmann constant, into T. There are 2 forms of ideal gas equation. This is in the form of number of moles, it is in the form of number of moles, and this is in the form of number of molecules. Okay, here Kb is Boltzmann constant. If you want to know the relation between Kb and R, let us move ahead. See, dear students, you can write mu is equals to number of moles, means you can say N, which is the number of molecules. Here I should write N, number of molecules. Number of molecules is equals to how many number of moles into mole value. So you can get mu is equals to N upon Na. There is another form. Just try to remember how many number of molecules are there in total is equals to number of moles into value of 1 mole. It is Avogadro's constant Na. Na is what? Value of 1 mole, 6.02 10 raised to the power 23. This is one form of the formula you can say of moles. Okay, now see what is the relation between these two, which we have already studied. PV is equals to mu RT and PV is equals to NKBT. These are two forms of ideal gas equation. Here you can say R is equals to Na into Kb, because if you will replace R with Na into Kb, you will get here, if you will replace R is equals to N into Kb, you will get mu Na Kb into T, and mu Na is what? Number of molecules. Okay, so you get this equation. So you get PV is equals to NKBT. Now let us move ahead. See another form of the ideal gas equation. Till now I have told you that you can write ideal gas equation as PV is equals to mu number of moles into gas constant RT, T is Kelvin, absolute temperature, and PV is equals to capital N, which is the number of molecules, Kb is Boltzmann's constant, into T. Always remember these two forms. Now see, mu is equal to number of moles is equals to total number of molecules upon, if we divide the Avogadro's constant, which is the number of particles in 1 mole. You can also write mu as the total mass of the gas upon the molar mass, m naught. Okay, mu, because see, if we use the concept of mole, then mu into m naught, okay, m naught is the molar mass, will give you the total mass of the object. How many number of moles into the mass of 1 mole is equals to total mass. If I use this here, what I will get? I will get PV is equals to, in place of mu I am writing m upon m naught into RT, and dear students, if I take V in the denominator, then it comes P is equals to 1 upon m naught. M naught is constant, molar mass of any gas is constant, m naught, R is constant, T is constant. If I take, then I get m upon V. It is equals to density. So the formula is P is equals to rho RT upon m naught. These are the three forms of the ideal gas equation which you have always have to remember. There are three forms of ideal gas equation. PV is equals to mu RT, PV is equals to NKBT, and P is equals to rho RT upon m naught. Now let us move ahead. We will come on to the derivation part, which is how much is the pressure exerted by an ideal gas on the walls of the container in which it is filled. So again, before going ahead, we have to take some assumptions, and these are called the assumptions of ideal gas. You are assuming, I should write here the assumptions of an ideal gas. We are assuming that a gas consists of molecules, and all molecules, the molecules of an ideal gas, are in incessant random motion. Incessant means continuous, incessant without stopping, incessant random motion. this is one assumption, and you have to write an heading, assumption of an ideal gas. Suppose you are having an ideal gas, a gas filled in a container, then you assume that all molecules are in random motion. This all gave by the scientist Maxwell. So he made some assumptions before going ahead. And then second assumption is all molecules are colliding with each other and with the walls of the container. All molecules are colliding. Colliding, it does not say कि they are hitting with each other. Actually, they are interacting, colliding with other molecules and with the walls of the container. And this collision is perfectly elastic. Okay, you have to write this collision is perfectly elastic. Now there is one more assumption you have to write is as the collision is perfectly elastic, the kinetic energy is conserved and the momentum is usually conserved. So I write the kinetic energy is conserved. It was the assumption which you have to take before going ahead, is conserved. Okay, right. Now let us move on to the resolution portion, which is the pressure exerted by a gas filled in a container. So to do this, first we assume there is a container like this, okay, and let us suppose the length is L and it is a cube, okay, it is a cube, and it is x-axis, y-axis and z-axis. Let us suppose here there is one molecule here, and this molecule is moving with some velocity inside the container. There are lots and lots of molecules which are moving, but we have to first study about one molecule, then we'll move on, then we'll make it a general assumption for all molecules. Let us suppose the velocity of this molecule is Vx, Vy and Vz, because it is moving in the 3 dimensions, so it is having x component, y component, z component. When it collides with the wall perpendicular to the x-axis, then what will happen? It will rebound, it will bounce back from here, and the velocity here, it will become, since the x component changes direction, so I can write here the velocity will become v minus vx, but the y and z component will remain as it is. There is no change in the y and z component. We are assuming that the molecule is colliding with the wall perpendicular to the x-axis, so only the x component of the velocity changes. Let us suppose the mass of this molecule is small m. Now what is the momentum which is changed in the ball? Now let us see. If the initial velocity was vx, I'm talking only about the x component, okay, initial velocity was vx, and the final velocity after collision becomes minus vx. What is the change in momentum of the ball? It is equals to final momentum minus initial momentum. Final momentum is m into vx, m into v, minus sign is already there, minus initial momentum is vx. It is my initial momentum and it is my final momentum, final minus initial. So the total change in momentum is minus 2m into vx. So the momentum transferred to the wall, momentum transferred to the wall during elastic collision, it is due to one molecule, is equals to plus 2m vx, because this is lost momentum, you can say change in momentum of the molecule. So opposite of it is transfer to the wall. Now we have to understand how many molecules are there inside the container which are colliding and transferring their momentum to the wall. So here this was my x-axis, and this was my y-axis, and this was my z-axis. Okay, and here it is yz plane, and the molecule was something like here, and this molecule was moving like this. Here, as you can see, if I'm assuming only on this x on this plane I'm talking about, which is parallel to the yz, here yz perpendicular to the x-axis, this plane is perpendicular to the x-axis, and it is in the yz plane. Okay, the y component of velocity will remain as it is, the z component of velocity remain as it is, only the x component changes direction. So we have to know how much is the number of molecules in the container which are colliding with the walls, so that if I came to know कि एक molecule है, one molecule which is transferring the momentum 2m vx, and if we know how many molecules are there which are colliding with the walls, then we multiply with this 2m vx, we'll get the total number of molecules which are colliding with the walls, and they are transferring their momentum. Once we know the transfer of momentum, then we can easily find out the rate of change of momentum, then force, then pressure. Let me recall you. We are going to find out the pressure. See, pressure is force upon area, and force is rate of change of momentum. Force is rate of change of momentum. Okay, rate of change of momentum, del P. Here we will write in place of del P, I can write del Q. Q or del Q, no problem. Okay, so we are going to find out first the momentum change by one molecule, then we will find out the momentum change due to number of molecules, then we will find out rate of change of momentum, then we will find out force, then finally pressure. Actually this whole chapter starts with what? You might have some confusion कि हम लोग कर क्या रहे हैं, हम लोग पढ़ क्या रहे हैं. सबसे पहले हम लोगों ने इंट्रोडक्शन में पढ़ा था बॉयल्स लॉ, चार्ल्स लॉ, एवोगाड्रोस लॉ. उसकी हेल्प से हम लोगों ने एक आइडियल गैस इक्वेशन PV is equals to mu RT, we derive this, then we find another form PV is equals to N kBT, and we find out the P is equals to rho RT upon M naught. Like this equation we are having rho RT upon M naught. Here rho is the density, R is the ideal universal gas constant, and T is the temperature, and M naught is the molar mass. इसके बाद हम लोगों ने क्या पढ़ा? इसके बाद हम लोगों ने सीधे से जंप लगाया सेकंड पॉइंट कि आखिर कोई गैस कितना प्रेशर एक्सर्ट कर सकती है. एक्चुअली द होल चैप्टर इज बेस्ड ऑन दिस कॉन्सेप्ट. आप लोगों को इसका डेरिवेशन आना चाहिए, मैं वही समझाने की कोशिश कर रहा हूँ. और ये किसने दिया? दो साइंटिस्टों का कंट्रीब्यूशन है, एक है मैक्सवेल, जेम्स क्लर्क मैक्सवेल, और एक है बोल्ट्जमैन. लुडविग बोल्ट्जमैन था इनका पूरा नाम, बोल्ट्जमैन. तो हम लोग इसको मैक्सवेल्स बोल्ट्जमैन के हिसाब से भी बोल देते हैं पूरा, मैक्सवेल एंड बोल्ट्जमैन. अब इन्होंने इसको डराइव करने के लिए क्या क्या एज्यूम किया. इन्होंने देखा कि भाई ऐसा है कि आखिर कोई गैस कितना प्रेशर एक्सर्ट करती है. इन्होंने एक माइक्रोस्कोपिक लेवल पर इसकी पिक्चर को डराइव करने की कोशिश की. आखिर मॉलिक्यूल्स मूव कर रहे होंगे, मूव करने के साथ साथ वो एक दूसरे को और बॉल्स को कोलाइड कर रहे होंगे, कोलाइड करने से इनकी एनर्जी वगैरह में कुछ चेंजेस होगा. तो आखिर कितना प्रेशर एक्सर्ट करेगी, प्रेशर के हिसाब से फिर हम लोग क्या करेंगे, फिर इसका टेम्परेचर डिपेंडेंस देखेंगे. फाइनली जो प्रेशर का फॉर्मूला निकलेगा ये आइडियल गैस इक्वेशन को सेटिस्फाई कर रहा था, इसलिए इनके लॉ को वैलिड किया गया. अब कैसे प्रेशर का डेरिवेशन हमें करना है. सी, सबसे पहले आप लोग क्या करोगे, कुछ एजम्पशंस लिखोगे. सबसे पहले अगर आपसे डेरिवेशन पूछा जाएगा तो देन यू विल राइट सम एजम्पशंस कि सभी मॉलिक्यूल्स कोलाइड वगैरह करते हैं, इलास्टिक है, एक दूसरे से इनको कोई लेना देना नहीं है, रैंडमली मूव कर रहे हैं, एंड देयर इज़ नो लॉस ऑफ काइनेटिक एनर्जी, देयर इज़ नो चेंज इन टोटल मोमेंटम. ओके, बिकॉज टोटल मोमेंटम इज कंजर्व. देन उसके बाद आप क्या करोगे, देन यू विल ड्रॉ दिस फिगर लाइक दिस, एंड आप यहाँ पे क्या लाइन लिखोगे कि एक्स कंपोनेंट की अगर हम बात करें केवल, तो उसका कितना चेंज हुआ वेलोसिटी में, रिबाउंड करेगा तो वेलोसिटी विल चेंज माइनस वी एक्स. मोमेंटम में कितना चेंज हुआ, माइनस 2m vx. कितना मोमेंटम वॉल को ट्रांसफर किया, प्लस 2m vx. इसके बाद आप लोग क्या करोगे कि टोटल नंबर ऑफ मॉलिक्यूल्स निकालने की कोशिश करोगे. अब टोटल नंबर ऑफ मॉलिक्यूल्स हम लोग कैसे निकालेंगे, वी हैव टू सी दिस. ओके, देखिए, अगर if in time del t, I'm talking about time del t, because a molecule will take time del t to move from one place to another place. There are many ways to derive this. And the molecule moving with velocity vx. Okay, the molecule is moving along x-axis, the velocity is vx. Now डिस्टेंस की अगर हम लोग बात करें, व्हाट इज द डिस्टेंस ट्रेवल्ड बाय, डिस्टेंस ट्रेवल्ड इज वी एक्स इंटू डेल टी. मैं ये कह सकता हूँ कि जो भी मॉलिक्यूल वी एक्स डेल टी डिस्टेंस में आते होंगे, क्योंकि वी एक्स इज द वेलोसिटी एंड डेल टी इज द टाइम टेकन टू मूव फ्रॉम वन प्लेस टू अनदर प्लेस. सो जो भी मॉलिक्यूल्स डिस्टेंस वी एक्स डेल टी में आते होंगे, दे विल कोलाइड. द मॉलिक्यूल्स in the range length, you can write in the length vx del t can collide with the wall. प्रेशर कैसे आएगा? जब वो दीवार को हिट करेंगे, वॉल को कोलाइड करेंगे. अच्छा, अगर हम लोग डिस्टेंस के साथ साथ पूरे वॉल्यूम की बात करें, अगर इसका एरिया ऑफ क्रॉस सेक्शन ए है, इस पूरी साइड का, प्लेन का, तो वॉल्यूम कितना हो जाएगा? ए वी एक्स डेल टी. या ये कह सकते हैं कि जो the molecules in the volume A Vx del T will collide with the wall. Okay, now let us move ahead. कि अब आपको इस स्लाइड का कोई सेंस नहीं, it was the revision part. Okay, see, if there are n molecules per unit volume, then the total number of molecule colliding with A is the area, Vx del T is the length, N is the number of molecules per volume, and I am writing this number of molecules. See, half of the molecules are moving to one side and half में move another side. हम लोगों को ये मानना होगा कि ऐसा नहीं है कि जितने भी मॉलिक्यूल हैं वो सभी एक ही तरफ, एक सी इसी डायरेक्शन में जा रहे होंगे. भाई कुछ मॉलिक्यूल इधर भी तो जा रहे होंगे. तो हम लोगों ने क्या किया, वी हैव रेज्यूमिंग, ही हैव एज्यूम्ड दैट हाफ ऑफ द मॉलिक्यूल्स आर मूविंग टू वन साइड ऑफ द वॉल एंड half are moving to another side of the wall. Okay, so I am writing here the total number of molecules hitting the wall, colliding the wall, is how much? Half. N is the total number of molecules per unit volume, is the area, Vx del T is the length. It is the total number of molecules. So the momentum transferred by these molecules is how much? सर एक मॉलिक्यूल कर रहा था 2 mvx, तो इतने मॉलिक्यूल कितना करेंगे? 1/n a vx del t, we will multiply. Okay, 2 cancel out each other, we'll get half, we'll get mvx and mvx is this na vx del t, na vx del t. It is what? The momentum transferred, and I am representing the momentum by sign p, or I can write here q also, because in gases you can take this. Okay, what is the rate? तो मैं del t को उधर ले आता हूँ. What will it become? n m a v x square. This is the rate of change of momentum. Now what is the force? It is equals to the force. What is pressure? Force upon area. अब मैं एरिया को भी नीचे ले आता हूँ, तो प्रेशर कितना हो जाएगा? एन एम वी एक्स स्क्वायर. फाइनली आपको ये पॉइंट समझना है कि अगर हम लोग कंसीडर करें कि हमारे पास कोई एक कंटेनर है, एक कंटेनर मैंने यहाँ बनाया है, कंटेनर है, और इस कंटेनर में मान लीजिए, लेट मी मेक इट अगेन. ओके, लेट मेक इट अगेन. This is x-axis, this is y-axis, this is z-axis, and no, not like that. If it is a container, and I am assuming it is y-axis, it is x-axis, and it is z-axis, it is yz plane, it is a plane parallel to yz, it is also a yz plane, okay. And here is the molecule which is going to collide with the wall, and whose velocity is vx, vy, vz, because it is moving along xyz, so it is having three components of velocities. See dear students, I am considering the collision of the molecule perpendicular to the x plane, x axis. This yz plane is perpendicular to x axis, so I am considering a molecule moving in any random direction, it is colliding perpendicular to the, it is colliding to the this plane, yz plane. Now you can easily observe only the x component is changing, yz will remain as it is. इस मॉलिक्यूल को नीचे आना है, अभी ऐसे हम मूव करेगा तो yz कंपोनेंट में कोई चेंज नहीं हुआ, जो वेलोसिटी y और z कंपोनेंट की थी वो सेम रहेगी. तो इनिशियल वेलोसिटी वाज vx and final velocity will become minus vx. Okay, the momentum is initial was mvx, the final momentum is 2 mvx. चेंज कितना हुआ मोमेंटम में, फाइनल मोमेंटम माइनस इनिशियल मोमेंटम माइनस 2 mvx, इतना चेंज हो गया. अब मैंने क्या किया था, इसके बाद चेंज निकालने के बाद ये देखा कि कितने मॉलिक्यूल थे भाई, एक मॉलिक्यूल के मोमेंटम में इतना चेंज हुआ, आखिर कितने मॉलिक्यूल थे. तो इसके लिए आप लोगों को एक थ्योरी लिखनी पड़ेगी कि डेल्टी टाइम में कोलाइड करता है, वी एक्स उसकी वेलोसिटी थी. तो अगर कोई मॉलिक्यूल इतनी वी एक्स डिस्टेंस में आ रहा होगा तभी वो कोलाइड कर पाएगा. और अगर हम एरिया का मल्टीप्लाई कर देंगे, मतलब कि इतने वॉल्यूम में, एरिया इंटू लेंथ इज वॉल्यूम, अगर इतने वॉल्यूम में कोई मॉलिक्यूल होगा तो वो कोलाइड कर रहा होगा, लेकिन आधे मॉलिक्यूल इधर से एक साइड जा रहे होंगे, आधे मॉलिक्यूल दूसरी साइड जा रहे होंगे. तो मैंने क्या किया, हाफ का मल्टीप्लाई कर दिया, और एन यहाँ पर क्या है, हाफ एवरेज ले लिया, कितने मॉलिक्यूल आ रहे होंगे, एन इज द नंबर ऑफ मॉलिक्यूल पर यूनिट वॉल्यूम, और ये पूरा वॉल्यूम हो गया. तो यहाँ नंबर आ गया, देखिए नंबर ऑफ मॉलिक्यूल पर यूनिट वॉल्यूम और ये वॉल्यूम, तो वॉल्यूम इसका मल्टीप्लाई करोगे, वॉल्यूम वॉल्यूम कैंसिल आउट, नंबर ऑफ मॉलिक्यूल्स आ गए. हाफ इसलिए लेके कि आधे मॉलिक्यूल इधर आधे मॉलिक्यूल इधर, तो कितने कोलाइड कर रहे होंगे वो हमको आ गया. हमने कहा कि मोमेंटम कितना ट्रांसफर करेंगे, सारे मॉलिक्यूल मिल करके, तो 2 mvx इंटू दिस वैल्यू. यहाँ से निकल करके आया कि दिस इज द मोमेंटम ट्रांसफर. सम बुक्स यूज टू राइट पी ऑल्सो, बट यस यू विल राइट क्यू. सी, अगर हमें फोर्स निकालना है कि आखिर ये गैस मॉलिक्यूल्स कितना फोर्स एक्सर्ट करेंगे वॉल पर, तो रेट ऑफ चेंज ऑफ मोमेंटम एंड यू डिवाइड बाय डेल्टी. एंड प्रेशर निकालना है तो एरिया का डिवाइड कर दो, फोर्स अपॉन एरिया एन एम वी एक्स स्क्वायर. दिस डेरिवेशन यू हैव टू रिमेंबर फॉर द एग्जाम्स. नाउ सी व्हाट नाउ happens. In this container all molecules are there, not all molecules are moving with velocity vx. I am taking only one component, then we will generalize to all components a common velocity. कुछ ग्रुप्स vx वेलोसिटी से आ रहे होंगे, कुछ ग्रुप्स की वेलोसिटी vx1 होगी, कुछ ग्रुप्स की वेलोसिटी 2 होगी, कुछ ग्रुप्स की वेलोसिटी v3 होगी, x3 x कंपोनेंट टॉकिंग अबाउट. तो हमने कहा सबकी मीन वेलोसिटी क्या होगी, तो आप लोगों ने क्या किया, इसकी वेलोसिटी को vx मीन ले लिया. ठीक है, अब हम लोग यहाँ पर क्या करेंगे कि जो वी एन एम वी एक्स स्क्वायर आया है, आई कैन राइट, आई विल हैव टू राइट हेयर वन लैंग्वेज दैट नॉट ऑल मॉलिक्यूल्स मूव विद द सेम velocity. There are some group of molecules you have to write in your own language. Some group of molecules are moving with one common velocity, another group with another velocity. So what is the overall velocity of all molecules? You can write is v mean, okay, vx mean along x-axis. So the pressure exerted by all group of molecules moving with different velocities vx and mean. This bar represents the mean velocity. सर आपने x कंपोनेंट तो ले लिया, y कंपोनेंट z कंपोनेंट भी लेते हैं सर, क्योंकि जो गैस है वो हमारी आइसोट्रोपिक है. आइसोट्रोपिक का मतलब ऑल मॉलिक्यूल्स आर मूविंग विद इन ऑल रैंडम डायरेक्शन. एंड मैक्सवेल ने ये एक एजम्पशन माना था कि जो x कंपोनेंट्स होंगे जितने भी, और जितने भी y कंपोनेंट्स की वेलोसिटी होगी और जितने भी z कंपोनेंट्स की वेलोसिटी होगी वो सभी इक्वल होंगी. अगर हम टोटल वेलोसिटी की बात करें, ये मीन वेलोसिटी का स्क्वायर चल रहा है एक्चुअली में. हम यहाँ पे केवल vx केवल vy केवल vz नहीं ले रहे हैं, मैक्सवेल ने इसमें vx स्क्वायर लेकर के वेलोसिटीज़ के मीन निकाले थे. तो ये क्या होगा कि x कंपोनेंट की वेलोसिटी, y कंपोनेंट की वेलोसिटी और z कंपोनेंट की वेलोसिटी मीन वैल्यूज़. सर ये तो सभी इक्वल है, तो मैं क्या ये कह सकता हूँ कि v टोटल मतलब मीन वेलोसिटी ऑफ होल गैस इज़ 1 अपॉन इस 3 टाइम्स vx स्क्वायर vx मीन स्क्वायर, या vx स्क्वायर इज इक्वल्स टू 1 अपॉन 3 v स्क्वायर. सी डियर स्टूडेंट्स, मैंने क्या किया यहाँ पर, जो x कंपोनेंट की वेलोसिटी थी मैं उसकी जगह अगर टोटल वेलोसिटी निकालना चाहूँ, दिस इज़ माय टोटल वेलोसिटी v, नॉट v something v mean square. Okay, 2 is here, मीन्स दैट कि एक कोई मॉलिक्यूल के लिए अभी हम लोग केवल एक्स कंपोनेंट की बात कर रहे थे. अगर मैं टोटल वेलोसिटी की बात करूँ तो वो वी होगी, ओनली वी मीन स्क्वायर. So if I use this and put in my previous equation, which was P is equals to N Vx square, I can write here pressure exerted by the gas molecules is 1 upon 3 V mean square, not 2 here, V mean square. Okay, it is a final formula of the pressure exerted by the gas molecules filled in the container. Here the v mean square velocity is the, you can say, the